Hi everyone, thanks again for being here. My name is Răzvan Craina and I'm one of the OpenSIPS developers. I've been with the project for about 8 years, 7 years now. I'm about to make 8 years. And today I will be talking about high availability and load balancing at the edge of your OpenSIPS platform. It will begin as a short story, but will easily evolve to a more technical one. We'll be talking about DNS. Probably all of you know what DNS is and how it works. We'll talk about VRRP, Anycast, and we'll see how all these link up in order to offer high availability and load balancing to your platform. So probably most of you are already using this kind of scenario where you have a bunch of asterisk server here. You have OpenSIPS in front of them just to, at the border, just to ensure access to your customers in your entire network and to your gateways. So there are multiple advantages of these scenarios. For example, you can impose security here. You can ensure aggregation of IPs, so you don't have to present to your gateways all these IPs. You simply present OpenSIPS IP, and that's it. Everything will go smooth. However, some of you might have seen crashes or something happens on this link and OpenSIPS goes away. How do you solve it? How do you sort this out? Well, the solution is simple. You simply put two or more instances and you're set up. If one goes down, then you have the other one. However, it's not that simple because you would ask yourself, which one do we tell our customers to use? Because here we have two instances, therefore we have two IPs. That's where DNS comes in handy. As I presume all of you know how DNS works, but I'm going to show you like a brief presentation. So basically DNS is used to resolve FQDN domain names into IPs, actually into services. It's considered one of the first distributed application. So this has been developed in 1985. So basically everybody knows about it, and most of the clients already support it. And it has several types of queries like NAPTR, SRV, PTR, whatever. So there are many, but today we'll be talking about these two. How DNS works is very simple. So imagine that you have a customer, you have your platform registered at example.com. You just tell your customer, here's your user ID, here's your password, register to example.com. What is your customer doing? What is the SIP client doing actually? It first does an NAPTR query to find out the services that this example.com platform has. And here you can see that it has two different services. One is over UDP, one is over TCP. Which one we choose? Well, that's where this field comes in. Basically, this is the DNS precedence and tells you, in case you have multiple entries, first choose this one. If this one is not working, then choose this one, the second one. So the lower the precedence is, the higher the possibility to choose it is. So as you can see, this somehow offers kind of a failure mechanism. In case this server is not reachable, then use this one. So this is the first step into failover. Next, we take this response and do an SRV query. What does an SRV query tells us? It tells us where the service is. So in this case, you can see that you have example.com serving UDP queries at SIP1.example.com and SIP2.example.com. Again, how do we choose them? There is also a precedence here, but in case these two precedents are equal, we go to the next field. This is the weight. The DNS weight is based to do a sort of load balance. So everybody will, for example, if these two values are equal, there are 50% that some of the queries get here and some of the queries get here. Furthermore, we just take this response, resolve it to an A query to find out the IP of the server. In this case, this is the IP of example.com, and simply forward send the registration there. This sounds really nice, right? Let's see how this works in practice. Unfortunately, in practice, it doesn't go that smooth. Why? Because let's say customers or clients usually register for longer periods, like 1 hour if it's a desktop or a hard phone. If they take 1 hour to register, what happens if the machine goes down, if the registrar goes down? Well, it happens that every single inbound call that reaches the server, it won't get to the client. So inbound calls will not be available. Of course, outbound calls will be available because the client implements the failover. If the client implements the failover mechanism, it will reach the server. And SIP being based on UDP, usually there are not that many mechanisms to find out whether the server is up or not. Some of the clients, the SIP clients, are doing pings, and if the server does not respond, they simply fail over to a different one, but most of them are not. And most of them don't have TCP support, because if they would have had TCP support, they would have immediately figured out the server is down and moved to a different server. So as you see, DNS does not provide any kind of high availability. If one server goes down, it simply has failover abilities. So we somehow need to register, to share the register information with the second instance. So, and I have here an example how that works. So imagine that you have your customer, you have a DNS response that resolves to 2 different servers, and you have a replication mechanism between these instances. Now, when the client registers, let's say it chooses this server. So it sends its registration information, and this guy stores it, and then forwards it down to this guy. So now both instances know the same thing. Both instances know where the green guy is. Therefore, if this goes down and a call comes, an invite comes, then you know exactly where the green guy is because you also have this information, right? Okay, so that being said, we need the application layer to be able to also support this kind of replication mechanism. Otherwise, failover and high availability wouldn't work, correct? And there are multiple types of multiple possibilities for doing replication. For example, you can simply replicate all the traffic, mirror all the traffic to all the instances. Well, this is not that efficient. You would probably have noticed. You can also use a shared database to share to have the shared information, to have the shared registration. So the 2 instances can point to the same database, and if one stores some information in there, the other one can simply read it. However, this means that you have to do real-time database query, and that's not efficient either. You probably don't want to do that. That's why in OpenSIPS we built a different a native replication channel that is built on top of the cluster module. So basically you can have as many instances as you want in a cluster, and you can share the information in a very reliable and very efficient way within that cluster. This is offered by the cluster module and the binary interface module. Bogdan talked about it in the previous presentation. I'm not getting into too many details because I've already presented this last year. Okay, what kind of data can we share? Well, as we have seen, we need to share the user location or the user registration information. We also need to share the ongoing or active calls, the dialogues, as they are called in SIP. We might need to share some rate limiting limitations. So for example, if you want to have a shared concurrent call limitations, so both servers need to share how many calls each of them have in order to have a global limit on the entire platform. So that's a kind of replicated data that you need. And basically you can share anything using some custom script functions. So that being said, this looks very promising, right? However, in practice it's not that promising. Because why? Because usually here there's a big wall, a firewall. What does a firewall do is basically when this guy registers, it opens here a pinhole that maps from this guy only to this IP. So if this instance goes down and an invite comes in, it will be blocked by this firewall, because that's how NAT works. So we need a solution. We need a mechanism to move the IP from here to here, right? Because otherwise, this guy, the firewall, will not allow any inbound traffic without the client opening a new pinhole to the new IP. That's what VRRP does. So VRRP it comes from Virtual Router Redundancy Protocol, and is used to monitor multiple instances and elect a single master node. That master node receives the virtual IP and all the traffic that is sent to that virtual IP. And there are a couple of solutions, very stable ones. They're very old, like VRRPD or Keep Alive. Both of them do the same thing, and both of them work on top of the VRRP protocol. The way it works, so imagine that you have multiple instances, and the first master node periodically sends pings to all the other instances, instructing them that he's available, he's alive, he can handle traffic. If one of the machines are missing those pings, he starts a new election algorithm, and a new master node should be elected. So this sounds promising. Regarding the previous problem, this might sort out, because as I said, all we need to do is move the IP from one side to the other instance, and we are set, because we will be able to break the firewall. In practice, VRRP, although it works really well, it might become a bit difficult to configure at first. Why? Because by default, VRRP is not used to monitor services. It is used to monitor machines. So if you, for example, only want to monitor the OpenSIPS service, then you have to write your own scripts, your own monitors and set your own thresholds and indices that indicate you whether OpenSIPS is up or not. And in case something is wrong, you'll have to give up the master label, let's say. Another thing that you have to take into consideration is that VRRP requires support from network equipment. So you have to be in the same multicast domain in order to be able to move the IP. That's because VRRP is based on the multicast protocol, and this multicast protocol is not routed in the internet. It's only routed in local network areas. So basically, you can't move an IP from one location to a different location unless you have basically a LAN between these two. But it works. I mean, we've been using it for a while, and it works really, really good. But is it enough? Let's see. So we have the previous example where the client is sending a register to this OpenSIPS. Both instances have the register information. And well, in order to keep this pinhole alive, you'll have to send periodically send pings, either from here or from here. We usually send it from here. That's because not all the clients know pinging. So that's why we are doing it. So we are sending pings and everything is fine. This pinhole is opened. However, this guy also has the registration information. So he also thinks that he needs to ping. So he will send pings from here. However, he doesn't own the virtual IP. So he will probably use a completely different interface that will be blocked by this firewall. And that's not the only problem. Imagine that you have like 10 instances of OpenSIPS. What if all of them would have pinged, would have tried to ping actually him? You'll basically have a lot of useless traffic. So that's why we also need the application layer like OpenSIPS to somehow partition the data, and we need a mechanism to tell OpenSIPS to stop acting on behalf of the replication data. So we need to tell this instance that you don't need to ping this guy because there's somebody else that's doing it. Also, when something goes bad and this guy goes down, you need the mechanism to tell him, now you can start to ping it, because now you have the virtual IP, now you are allowed to go through the firewall and maintain the pinhole, right? All of this is already done in OpenSIPS using some simple MI commands, so you don't have to go into too much trouble, because there are other solutions like adding IP tables rules to prevent this guy from pinging, but there's still some processing, some useless processing that's done. We can get rid of that using OpenSIPS and some simple MI commands. There are also other pitfalls, like the virtual IP is only pinned to a single IP because there's only one IP that can, there's only one machine that can get traffic for a single IP, right? You can have it assigned to multiple machines. But if you do that, you will probably need to disable the traffic. Otherwise, the machines will start to take each other's IP. The ARP table will go nuts, and you don't really want to do that. So you have to you'll have to set up some IP tables rules to prevent others' machines that already have that IP from processing traffic. Again, traffic goes to a single machine, so all the others' machines are just standby. So this might look like a waste of resources, right? You can also do a master-master. So for example, if you have 2 instances, you can do a master-master setup, but you will need multiple VRRP instances, and you need to play with the IP tables rules in order to move them to always disable the IP tables rules from the active machine and enable it on the backup one. So it's not hard. It's not that hard. It's doable. We are using it, but you might run into some issues. And again, the IP being assigned to a single machine is not that efficient because you can't really do load balance. You can only simply send registration like SIP traffic to one single machine, and that's it. All the others are standby or can process traffic for that specific IP. And that's where Anycast comes in handy, right? So what does Anycast mean or do? Do you know? There were a couple of presentations about that this year too. So basically you have the same IP assigned to multiple machines, actively assigned to multiple machines. And each machine can act on behalf of that IP, so each machine can process traffic from that IP. This is a very, very easy way to balance traffic. It's usually implemented over routing protocols like BGP. So imagine that you have an IP assigned. Actually, I have it here. So imagine you have 3 instances. All of them have here, towards your customers, a single Anycast IP, right? So all of them have assigned on their machines the same IP. There's a router here that advertises routes to all 3 machines. So when an invite comes in, it is sent based on a distance metric, because that's how routing works, based on a distance metric, it is sent to one of these machines, one of these instances. And from that on, you can use Unicast here or Anycast, whatever. But I am using now Unicast IPs to keep it simple. Now, we have an invite that goes to an asterisk server. The asterisk server responds, sends a 200 OK here, which is further sent here, right? How do we route this 200 OK? How do we make sure that the 200 OK goes through this instance and not through this one? Well, here we have the unicast address, so the reply will always go here. We can't go to any other instance, at least not in this scenario, because we are using unicast IPs here. So the call is responded, and we send here the 200 OK. This guy is happy, somebody answered his call, and he's sending an ACK. Well, now the ACK, according to the routing protocol, and because here is an Anycast IP, the ACK might get on a different server. Well, we get here, how do we know to send it here? Well, that's simply record routing mechanism. So this is really simple. And now this guy is happy, this guy is also happy, so the call establishes correctly. However, what about this guy? This guy didn't get the ACK, right? So he will start wondering what happened with my ACK. He's not able to complete his dialogue because he didn't get the ACK. That's why we need a mechanism to share dialogue information between all these instances. So this guy, when he starts the dialogue, he needs to tell this guy, well, there's a new call from here to here, and these are all the metadata. When this guy gets the ACK, it finds the dialogue, the call, it completes it, changes its state, like saying that the ACK was received, and needs to tell this guy, well, you have the ACK has got here, so you are free to, you should also update your metadata. Right, and everything works. Again, when a byte comes in, it might be sent to a different instance, right? Well, we also route the byte according to record route, so we will know the byte will end up here. But again, these three guys should replicate this byte event to all of them so that all of them can close their active dialogues. And everything is sorted out, right? How can we replicate? As I said earlier, we can use the cluster module, which is doing replication in a very, very efficient way. All we have to do is provision each instance in a cluster and tell the dialog module to replicate that information in the cluster. We only replicate dialog events, so it is very, very efficient. So we don't replicate like entire messages or stuff like that. And it's done using the binary interface. Again, I won't be talking about that. That's not it. Let's see why. So going back to our example, we've seen what happens if this guy initiates a call, right? What happens if this guy initiates a call? Let's see. So let's say it chooses the same instance. Well, it will choose the same instance. Why? Because here is a unicast IP. And the invite goes here to this customer. However, when it sends a reply, the reply is not necessarily landing on the same server. It might go over here, and we will get it here. Well, again, based on the transaction module, we know exactly where to send the reply. Well, this raises some completely different problems, because in this case now we need to replicate a completely different kind of data. We need to replicate transaction data. And that's not that easy. What happens if we don't do it? Well, this guy hasn't received 200 OK yet. So what happens if you don't receive a reply? you start retransmitting. So this guy starts sending again invites to this guy. This receives the invites and starts sending 200 OK probably here, and basically you get a lot of useless load. So we need to find a way of replicating transactions. However, this is a bit problematic. Why? Because a transaction contains a huge amount of data as opposed to the dialogue. For example, you'll have all the caller and call information. You also have that in the dialogue, but you have all the branches information. So for example, if you're doing something like a parallel forking and you have like 10 destinations, you probably you need to store and replicate information from 10 different destinations, as opposed to the dialogue. In a dialogue, you only have only the successful leg, right? So it's way more information. And also for transaction, you need to replicate the full messages. Why? And that for each leg. You need it because if one of the callees do not reply, then you need to retransmit again. So you need all the instances need to share all this information. So you end up sending like a few kilos of data for every single call. And this is not something that the data is very volatile. For example, invites, so this data needs to be replicated within in less than a second. For example, you might receive a provisional reply immediately after you send an invite. Also, for buy transaction, the buy transaction lasts less than a second because you send the buy, you receive the 200 OK, and that's it. But you still have to replicate this information to all the other instances. So it's very, very it's a very traffic consuming and processing consuming issue to solve. And we also need to coordinate who's in charge of retransmissions, because otherwise we'll end up in the same situation with the registrations, right? Everybody will try to retransmit everything and basically will flood the client. That's how we try to sort this out. We give it a thought and try to sort it out, and we ended up with two different solutions. One of them is using a lightweight. We call it lightweight Anycast. So imagine that you have here an invite that's sent to the client and goes through this OpenSIPS instance. So this guy stores the transaction information and that's it. He doesn't replicate anything. When a 200 OK comes in, you simply replicate the event, the metadata here, saying that, OK, I've got the 200 OK. You don't have to do any more retransmissions here. And simply pass further the 200 OK. So this looks like a very simple solution. The transaction is stored only where the request first gets in. Only events or state changes are replicated, so you don't really replicate all the messages, as I said earlier. And it's also, everything is replicated using the clusterer and binary protocol, so everything is very efficient. The pros for this solution is that it's very fast, it is lightweight, so you don't have to exchange huge amount of data and information. But the cons is that if the initial machine crashes, he's the only one that knows about the transaction. So basically everything will, the transaction will be lost and the call will not be able to be answered. Another thing that that's a limitation is that you can't really do anything on those replies, because here the reply, all the transaction information, you have it here. So this guy doesn't really know what kind of changes to do on this message. He simply relies it back, and that's it. So as I said earlier, this is a good solution. It sorts out the problem, but not entirely. That's why we thought of a different solution, like a full Anycast solution. where we have the same scenario. An invite gets here, we store the transaction information and send it further to this guy. The 200 OK gets here, but now instead of only replicating data, we replicate the full SIP message. Oops. Okay. When this guy gets the full SIP message, it will send a 200 OK here, and everything will be sorted out, right? So this guy doesn't need to know about the transaction. It's all this guy. So again, the transaction is stored only where the first request gets in. This instance receives all the messages related to that transaction from wherever they get. So any instance can get a reply. It will simply forward it to the main instance. And messages are sent again over the efficient binary protocol. This allows us to build more complex scenarios because having received every time the reply where the transaction stands, you have all the information to perform any changes on that message. So basically, this is how we offer a full failover and high availability solution. However, the cons are that there's more information to exchange because every single time we don't export only the event, but all the message received. All right, so let's do a small wrap up. So again, DNS, although it provides a failover mechanism, it doesn't really have any high availability considerants. Although it also provides some load balancing mechanisms and is supported by most of the SIP clients. Well, actually not all of them, but most of them. There's also some nice DNS extensions, for example, like geolocation. You can pick up a server based on the location of the IP. So you can get the server that's closer to you and do failover in case that goes down. And so DNS is quite an interesting and a must-have solution in your network. Also, VRRP is a very nice solution that we've been using again for a while, and it is used to move IPs from a failed machine to a new one. This way, we provide high availability. We can have multiple machines that share the same IP. We also have solutions to solve the network constraints. However, it does not offer very good load balancing abilities. That's why most of the time we need Anycast to provide both load balancing for internal edge proxy and failover and high availability support. It is relatively easy to implement. However, it is connectionless, so this means that all the applications that share this, that use this mechanism, need to somehow have a method to replicate data between them. Luckily, OpenSIPS already does that. So bottom line, in order to have a fully failover enabled and high available platform, you have to have your clients, they need to fully support the DNS logic, the SIP DNS logic. You also have to control your network layer in order to handle either VRRP or Anycast supports. But also the application layer needs to be aware of the data it uses and it replicates. And this is done very easy by OpenSIPS using the cluster module and in the binary protocol. You also need the application layer to coordinate which instances are responsible for the replicated data, because otherwise, if everybody thinks that he's in charge of that data, we will end up with huge loads of useless traffic, and we don't want that. So, as I said, there's no secret tool. There's no single secret tool to build a reliable and efficient VoIP platform. All you have to do is study solutions, put them together, and see and achieve what you want. Thank you very much.
Thank you very much, Razvan. Does anyone have a question that they would like to ask? All right.
Can you tell me which module is used for that?
Which one?
Which module we will use for that?
For Anycast?
Yes.
We will. This will be built on top because it's not already available. These are only the solutions that we discussed and we are going to implement. They will be available in the transaction module. So basically, I think everybody uses the transaction module.
Okay. What will be the name of the module so that we can
It's
search
TM.
for it? Pardon?
TM module. OpenSIPS TM.
TM.
module. Right.
Okay.
All right, other hands.
Over here in front.
Oh, thank you.
Okay, so this is not generally available yet?
Yet, yeah. It's actually ongoing work.
It's ongoing work, okay.
And
I'm just also curious about the message passing done at the transaction layer.
right.
How do you do that?
Well, basically, we use the binary protocol, which is used as a generic message passing protocol between OpenSIPS instances to pack the information from memory and send it to all the other instances.
Oh, is that done via some kind of message passing?
Right, right.
Which one do you use?
It's not. It's a native one. It's built by us.
Oh, okay. Okay, thank you.
Yeah, we.
All right, other hands. Here we go.
Has any thought been given to replicating presence across the
Yes,
cluster?
that's the next on our list. It's not there yet, but it's on top of our list.
And is there any thought about distributing the Anycast with servers in separate physical locations?
That's something that has to be taken care of on the network level. So if the network
So if they were
level
public
allows it, then
BGP
OpenSIPS will be
IPs.
able to, yeah, right.
Right. Okay. Thank you.
Back there.
All right. Oh,
There's one back there.
Simple question. What's the timeline when it'll be available? Any clue?
I think it will be available on the next release, and that's going to be next year in May. That's when we usually do releases. So it's probably be available by the end of the year. I'm not sure how that's true, but it will probably be available. The next release will be in May, so that's when you have it stable. There was also one question here.
is there anyone else? Questions, hands in the air? Yell at me if I'm not looking at you. All right, up here.
Actually, two questions. One is, what's your target for having consistency across all your nodes with this protocol? And then, secondly, if I recall right, on your full Anycast, you were just replicating the message back to the main node.
Right.
But what happens if that main node goes down? The other nodes didn't seem like they had state unless I missed something.
Yeah, we probably need to build a different logic for the transaction, but only so we don't need to replicate the messages this way because the messages will still be here and will be retransmitted by this guy. Actually, yeah, you need.
If the one on the left goes down,
right? I know.
After the invite's shipped, I mean, then there's no
yes,
awareness.
You somehow
of that
need to change the owner of the transaction. So
Right.
in order to change it, you'll probably have to replicate the entire transaction.
Over.
You're
Okay.
right.
But then how long will you? What's your goal? Because SIP transactions, especially if it's very local, it's very quick. So I mean, what's your target for getting a message from one box processed in the tables on the other box? From a transmission time, are we just talking a few milliseconds, or are we talking?
Yes, ideally it will be less than a few milliseconds.
Okay.
Ideal, but that depends on the network. It's not like something that we can control.
All right, other hands. No hands, no hands. All right. Razvan,
Thank you very much,
thank you
guys.
again.